Hey guys, what's up? Welcome back to our video series where we're talking about equilibrium existence proofs. This is just a different example for an exchange economy. So let's just get started. So we're going to have this function z, right? And that's going to map this triangle to a k-dimensional real number space, where this triangle here, like we said in our previous video, is our price simplex. That means that we have our price vector, right, is in a non-negative real number space. And the sum of all the individual prices in this price vector sum up to 1. And we're going to say if that's a continuous function and it satisfies Walras's law, right, that is if we have a price multiplied by this z function, that's going to be equal to 0. Then there exists some p such that the excess demand function z, right, is going to be less than or equal to 0. So let's go and prove this. So step number 1 is that we're going to normalize our prices. This is already done in our question, so we don't need to go and worry about that. Next, we're going to go and define a mapping G, which goes and takes values from our price vector and maps it to itself, right? And we're just going to pick what this function is going to go and look like. We're just picking. That's it here. And that's going to be defined as follows. With this Z plus P, right, is going to be defined as this vector here, right, which chooses the maximum value between excess demand and 0 here, right? We're going to consider some mapping G of J in our vector of G of P, right? So just to go and make this more explicit, right, G of P is a vector that goes and has many of these functions inside of it, right? And we're just going to pick one of them there. This mapping, right, is continuous, right, since this z plus term, right, is non-negative and closed and bounded on our price simplex. Thus, we can go and appeal to Brouwer's fixed point theorem, right, which is our step number 3. Appealing to Brouwer's fixed point theorem, we can do this because g of I, as previously stated, is continuous, and that the sum of these terms sum to 1, right, so it's closed and bounded. Therefore, we can say that there exists a p bar, right, such that if we were to go and plug in this p bar, we would go and spit out a fixed point for itself, right? Rearranging this, we go and we get the following. And the thing that we're going to do next is that we're going to multiply both sides by zj here, right? This is a little bit different from our previous proof because we're just going and working at this directly here. Continuing, we then go and run the summation operator over all j. This allows us to go and use Walras's law right here. So this goes and gets knocked out to 0, right, due to this guy here. Thus, we go and we have the summation of zj as a function of p bar, right, which is our fixed point, times z plus, right? We should put a little j here and a bar here just to go and clean that up there. That's going to be equal to 0. One thing that we have to note about this relationship, right, as guided by this arrow right here, is that every term is either 0 or zjp squared, right? And since we're choosing between the maximum between these two, any term as the sum is strictly greater than 0 or is 0 itself, right? But if it was the case, then the quality would not hold. Thus, we go and we must conclude that this must be true, right? That z here must be less than or equal to 0, but this time it really is supposed to hold with a strict equality right here. So we've already proved that there. So this is our second example in our series on equilibrium existence proofs for an exchange economy. I will see you in the next video. Take care.